Yeah, welcome to this small presentation on Kirchhoff's law. So first of all, we've got a small circuit here. I'm going to draw down what the circuit looks like in a minute. And when we look at Kirchhoff's law, we typically have different power supplies. And let me just show them to you. We've got one power supply made up of two 9-volt batteries. I don't know whether you can see them. Yeah, you can just about see them. And then we've got another power supply made up of just one 9-volt battery. So we've got 9 volts here, and then on the other side we've got 18 volts. Yeah, we can quickly test it out. Okay, I'm just going to get my meter going, just checking whether you can see the meter. You can just about see the meter now. Okay, let's have a look. So we put our leads to the front and to the back. And you can see we've got 9.4 volts. And when I go to the other side of the power supply, and if everything is being plugged in right, we've got 18.25 volts. I hope you can see this on the camera. Okay, so now we have to sort of deal with Kirchhoff's law. And what I'm going to do is I'm first going to take the measurements, and then I'm going to do the calculations. And if the calculations are right, measurements, unless you measure at the wrong points or there's a problem with the circuit, they don't lie. So let's have a look. We've got the resistors here. So this resistor here is a 220 ohm resistor. That resistor here is 330 ohms, and that resistor is 100 ohms. So we've got a current coming from these batteries, going into this resistor here, feeding the 100 ohm resistor, and we've got a current coming from this battery, doing the same thing, going through this resistor and feeding the 100 ohm resistor. So we've got two currents going in there, so both currents are going to be combined. They're going to come out here and they're going to split up to either the battery pack or the single battery there. Okay, first of all, let's have a look at the voltage drop on the first resistor. So that's a 220 ohm resistor. That's a 3.8 ohms, let's say 3.9 to round it off. Then we're going to look at the voltage drop here. So we've got 12.6 volts. Just let me repeat this and correct this. We've got V1, or the first voltage is 3.85. Then we've got 12.5 on our 330 ohm resistor. And then across our 100 ohm resistor, we have got 5.53 volts. Yeah. So again, 3.8, 12.5 volts, and 5.5 volts. Using Ohm's law, in theory, we could just calculate what current is going through each resistor. But we're going to use the different methods, mathematical methods, of coming to a conclusion of what currents are there. But let's measure the currents, and then we know for certain what currents we are talking about. I'm going to disconnect the 100 ohm resistor, put it on a different truck. I'm going to put a fly lead on the same truck. And put a fly lead here as well. So I have to break the circuit in order to measure the current. I'm going to go to my milliamp range. And let's see what we get. So I have to hold them. We get about 55 milliamps, 55.5 milliamps, 56 milliamp. And that's the current through the 100 ohm resistor. So that's a combined current from both sides. It's 55 milliamps. Okay, let's measure the currents through both resistors, individual resistors. So I've written them all down, these measurements, so I'm going to write them down. They've changed a little bit, a few milliamps, but that's just normal. It's the batteries, they go down a bit, so it changes. So I'm going to take the 330 ohm resistor out, and so I'm going to put a fly lead in. And it doesn't stick very well, but we're going to try. And I'm going to put another fly lead in here as well. Okay, so that's the 300 ohm resistor that comes from the 18 volt supply. let's take a measurement. We get 38 milliamps, 38.4 milliamps. I measured it earlier, it was 38.8 milliamps. So the batteries are going down a little bit. And now we're going to take a measurement from the 220 ohm resistor and measure the current for that one. So that's the one that comes from the 9-volt battery. See what we get from there. So again, I'm going to stick it in the lead, and if all the connections are there, it should work reasonably well. I get, whoops, the wrong way around. I get 17.45 milliamps. I did a measurement earlier and I got about 18 milliamps. Yeah. Okay, so my batteries have gotten a little bit down, but not to worry. So you can see the circuit. A quick description: 9-volt battery here goes into a resistor, feeds into the common 100 ohm resistor. Here we've got 18 volts, goes into a 330 ohm resistor, and again feeds to the same point. Now what Kirchhoff is saying is, he has got a couple of ideas that all voltages will equal 0. So we've got a voltage here, and then we're going to get a voltage drop here, get a voltage drop there. So if we subtract the voltage drop from this voltage, we get 0 volts. And we've got 18 volts here, so all the voltages are dropped on this resistor and that resistor. So we come down to 0 volts as well. So we have got some equations we can do, and we can play about with the mathematics a little bit. All the currents, which combine, they all currents which flow into one junction come out of one junction. So that's another of Kirchhoff's laws. So there are 2 laws, the voltage laws and the current law. And and that's what we find here. So we've got a current from these batteries, current from that battery, going into that resistor and coming out and producing a voltage drop. Okay, I'm going to leave it at that. So you've seen the measurements, and obviously you can take the film back. I'm just going to move this out of the way. And we're now going to do the mathematics. And I'm quickly going to show you how it's all done. I just need to check whether you can see all of the paper. Yeah, you can see it. We're going to start off with the circuit. And this is what the circuit looks like. So we've got our power supply. So that's 9 volts, which we've got here. Then we've got a resistor up here, which is my 220 ohm resistor. Yeah, so I'm going to write down 220, a little omega sign. And then we have got another resistor, which is my 330 ohm resistor. And then we've got our 18 volts power supply. Okay, so that's our circuit so far. Both power supplies we've got 18 volts here. They're all joined together as one earth, as you could see on the breadboard there. And then we've got a resistor here where both currents flow in together, and this resistor has got 100 ohms. A little omega sign, and we've got 330 ohms up here. We've got a bunch of currents. We've got I1, that's I1. And then we've got another current here, that's I2. And then we've got one current which goes down here, which we call, that's a combined current, which we call I3. Okay, I hope you can see this okay. Let's take the measurements, and I'm not going to take the measurements I measured right now, but I'm going to take the measurements I measured before, because I've written them all down, I can't remember the others. So we've got, first of all, I3. When I was taking the measurements earlier, I got 56 milliamps. And then for I1, I got 18 milliamps. I think what we measured was very close to the figures I got before. And for I3, I got 38.8 milliamps. Okay, let's have a look at the voltages. So we've got V1. So that's the voltage across our first resistor. So that's V1. And V1 is 3.9 volts. Again, I measured this earlier. Then we've got V2. And V2, that's over the 330 ohm resistor, is 12.6 volts. Bear in mind, we've got 18 volts which are dropped across the circuit, so it's quite a bit. And then we've got V3, and V3 is 5.58 volts. Yeah? So we've got all our voltages. Yeah? We can make a couple of statements, and I made one mistake here. Let me just correct this. So that's I2. So we've measured this stuff, and according to Ohm's law, or to Kirchhoff's law, the current law, is that all the currents going into this junction here should come out as well. So if we've got a current here and a current there, it's no other way for them to go than through this one, and we should get what we've measured, really. Okay, so let's have a look. We've got this formula, which is I3. This current here is equal to I1 plus I2. And when I sum this up, so we've got I3 is equal to 18 milliamps plus 38.8 milliamps. So when I add them both together, I get 48 plus 8 is 56 and a little bit, 56.8. That's near enough. We just call it 56 milliamps. So we've proven this because we've measured this. So we know this formula is correct. Okay, this formula is fine. No. Okay, now we have to come up with our equations and see what's going on in this circuit here. We have to assume when we do our equations that we have a voltage drop, or that our current goes a certain way. Yeah. And sometimes we don't know whether we are right or not, because when you look at this current supply here, or this power supply here, it could be the other way around. So instead of having plus and plus to the top side, it's pretty safe to say that the current is going to go that way, yeah, and this current is going to go that way. It could be the other way around. So if I had to reverse this power supply, and so we would have plus down here, and the current would go up, and this current would go down, we wouldn't really know, which way the current is going to go in I3, whether it's going to go that way or it's going to go up. But we would have to sort of run some figures or do some measurements. And a meter would tell us, we could measure it, but we could also calculate it. Okay, now this is all about calculating Kirchhoff's law, and we make it very simple to start off with, and then maybe in another video we can use the same circuit and reverse the polarity of maybe the 18 volt supply and see what happens then. Okay, let's have a go. We've got an assumption, and we assume that the current flows in this direction. We do the same here as well. So we've got loop 1, and this is going to be loop 2. Yeah. So we've got two loops we can work with now, and we can build our equations based on these two loops. And again, Kirchhoff says that all voltages equal 0. So we've got a voltage drop here, a voltage drop there, minus a voltage drop from the supply gives us 0 volts. Now, what is the formula for volts? The formula for volts is V is equal to I times R. Yeah. So if I say 220 times I1, that would be the voltage drop, should be V1. Okay. Right. Okay, let's start with our equations and sort of start playing about a little bit with Kirchhoff's law and later Ohm's law. The first equation, when I look here, I've got a voltage drop across this resistor here, the 220 ohm resistor. That's for loop 1. And I've got a voltage drop across here, across my 100 ohm resistor. And both voltage drops should equal to 9 volt. But because I don't know the voltage, other than having measured it, but mathematically I haven't got a clue what the voltage is across this point here. And because there are two currents flowing in this resistor here, so I don't really know what the voltage drop across that resistor is. So it's not as simple as saying, yeah, okay, everything is going to be okay because I just use Ohm's law and I calculate this loop. It doesn't work, yeah, because there's another current going in there as well. Actually, I put this loop the wrong way around. Let me put it the other way around. Because we start here and then it goes that way around. Okay. Okay, so we've got two currents flowing into this resistor. That's our assumption so far. The first equation which we're going to do is we'll add them all together. So we start at this point here. So we've got 220 times I1. So we've got 220. So we're going to calculate loop 1 here. 220 times I1, and then we add plus 2 200 plus 100 times I3. And that equals, we have to subtract 9 volts to get our 0. So we drop 9 volts here. So that's going to be minus 9. And that equals 0. So all voltages should cancel out. So that's my first loop. I'm going to do it for loop number 2. Loop 2, we're going to have a look at this loop here. Apologies, I decided to do, it's obvious that the current is going to go up here and it's going to go down, and both of them are together. So they're not opposing currents, but opposing currents is quite interesting as well. We're going to do this the next time round, so I was thinking a little bit ahead. Another example. Okay, so we're going to do this loop. So we start off with 330 ohm resistor. So we've got 330 ohms. And then our voltage drop will be I times R. So this is going to be I2. So I've got I2 here. And then plus 100 times I3. And then we drop 18 volts. So it's going to be minus 18 volts. And that's equal to 0. So I've got a voltage here. I've got a voltage there, and a voltage there. And if I take these voltage drops and then drop another voltage here, that's minus 18. So it should equate to 0. Okay, so we've got our two equations. But when I look at these two equations, we've got 3 unknowns here, which is a bit of a pain to deal with. So it would be nice if, when I look at these equations, I've only got 2 unknowns. But we've got this magic formula here, where you can see, that's the magic formula here, that I3 is equal to I1 plus I2. So I can substitute this I3 with I1 plus I2. Okay, I'm just going to start this on a new page. And we're going to do this. Yeah? So we're going to start substituting. Let me just push this out of the way. So I'm going to substitute. And first of all, I'm just going to deal with loop 1. I'm just going to describe here loop 1. That's what we're going to deal with. And we're going to substitute and simplify. And then we're going to deal with loop 2. And then we'll do a simultaneous equation. Okay, because everything equals 0. Okay, so the first one is we substitute this, and so we write our equation down. So nothing changes with so far with I1, so that's still the same. But then I've got plus 100, and what we've seen here is we've got I3 is equal to I1 plus I2. And because we don't like to deal with too many unknowns, we're just going to put in brackets I1 plus I2. Yeah. And that equals the minus 9. Yeah, so that's the last voltage drop. And that equals 0. Okay, let's open up the bracket. So I've got 220 I1. Yeah, and then when we look at the bracket, we have to multiply everything in front of the bracket with everything in the bracket. So we've got 100 I1 plus 100 I2 minus 9. That equals 0. Yeah, but bearing in mind, so when you look at these expressions here, in effect, they're all voltages. Yeah? We are just using the resistance, which is R times I is equal to V. That's good old Ohm's law. And so this is a voltage, that's a voltage, and that's a voltage, and that's a voltage as well. Yeah? We're using the Kirchhoff's voltage law to create or generate this equation. I'm just going to add these equations together. So I've got 320 I1, yeah, so that's putting these together, plus 100 I2 minus 9, and that's equal to 0. Okay, so we've got loop 1. Let's look at loop 2. And again, just to remind you, loop 2, we start off at our plus 18 volt supply, then we've got the first voltage drop here. So this is I2 times 330 ohms, and then we've got I3 times 100 ohms. So that's our loop. We're just going to write down what the equation for loop 2, and then we're going to substitute I3 with I1 plus I2. Yeah. Again, I3 is equal to I1 plus I2. So if anywhere where I see I3, I can instead use I1 plus I2, and it should be the same thing mathematically. Okay, let's give it a go. So we've got 330 I2 plus 100, and now instead of writing I3, I'm going to write in brackets I1 plus I2, because we have determined that that is I3, minus 18, so that's the voltage, and that's equal to 0. Okay, so we have done this, and now we're just going to open it up. So we've got 330 I2 plus 100 I1 plus 100 I2, and that's minus 18, and that's equal to 0. Right, what have we got here? We've got lots of I2s. So I've got 430 I2s. So I add them together. I just heard a beeping noise, but that was the meter, I think, just a warning noise from the meter. I don't know whether you could hear this on the camera. I thought the camera was about to shut itself off, but we are still okay. Okay, next we've got plus 100 I1 minus 18, and that equals 0. We can then, jiggle about our formula a little bit. So we've got so that the I1s and I2s are in the right place. So we've got I1 plus 430 I2 minus 18 is equal to 0. Now I've got two equations. Okay, let's have a look. We've got two equations, and the beauty is, instead of having three unknowns, we've only got two unknowns, and we can now use a simultaneous equation. Okay, what I've said here is I've got the equation from loop 1, which is 320 I1 plus 100 I2 minus 9 equals 0, and then we've got this one as well. So I've got 100 I1, 300 and 430 I2 minus 18 equals 0. So what I can do is I can do some magic here, because ultimately I want to get rid of this 320 here. And so if I multiply this whole expression by 3.2, okay, 3.2, what will happen? So we've got 320 I1 here, and this will also go to 320, but I have to multiply everything by 3.2, including the 0, but 0 times 3.2 just stays 0, so nothing much changes. Okay, let's do this and multiply this side by 3.2. So we have got, after doing this, um, 320 I1, yeah, plus 1,376 I2 minus 57.6. Bear in mind it's times 3.2, so we get a funny number coming out of it. And that's equal to 0. Okay, now I've got two statements here. I've got that's equal to 0 and that's equal to 0. So in theory, what I can do is I can just write this and then write this on the other side. Let's do this. It's going to be a really long thing, but you can see what we are doing. So we are now trying to resolve this equation through elimination. And all we've done is we have taken the factor between I1, and what we are looking for ultimately is I2. Okay, bear with me. You will see how the magic works. So what we're going to do is we'll write this out really, really long. So we've got this equation for loop 1. It's 320 I1 plus 100 I2 minus 9. And that's equal not to 0, but we know that that expression from loop 2 right at the bottom is equal to 0 too. So we know that whatever is on the other side of the equal sign must be the same as what's on this side of the equal sign. Okay, so we use 320 I1 plus 1,376 I2 minus 57.6. That's it. That's the end of the equation. Okay, what can I do? So on both sides, I can do an operation and I can subtract 320 I1. Let's do this. So we subtract 320 I1. So if I subtract 321 from this side, let's put the equal sign here. So all I'm left with is 376 I2 minus 57.6. Do the same here. So if I subtract 320 I1 from here, all I'm left with is 100 I2 minus 9. Okay, so I can move all the I2s to one side and the numbers to the other side. So I subtract what are we going to do? I'm going to subtract the 100 I2. So we're going to get subtract from both sides. So this is going to eliminate that one. So I'm going to get 1,276 I2. Then I add 57.6 and I get 48. So minus 9 plus 57.6 is 48.6, and it's nicely, everything is positive. So the last step we need to do is we need to divide 48.6 by 1,276, and we get I2. And I'm running out of paper. I'm just going to get the result here. So I2, if you run it through your calculator, is going to be equal to 0.038, and that would be I2 is equal to 38 milliamps. Yeah. Let's have a look what we measured. We measured 38.8 milliamps, so that's very, very close. And we have calculated 38 milliamps. Yeah. We can now sort of obviously calculate the rest by just sticking everything in the different formulas. Let's. How much time have we got? We haven't got much time. Let me just show you. I hope you can see this. Let me just see. Just trying to zoom in. Okay, so I've done the figures here. I think you should be able to see them. So I've put them into both equations. We've got several equations where we can try this with. And they should all give us the same result. So for I3, I got, let's have a look. Let's do the first equation here. So we get for I1, 16.25 milliamps. And that's using one equation. Using the other equation for loop 2, so this is, I think it's loop 1, if I got it right. This is the equation for loop 2. I substituted I2 with 38 milliamps, and we get the same figure, 16.2 milliamps. And that's really what we should get. And then once we've got our two currents, we can calculate, we've got I1 and I2 now, we can calculate I3. So we add them both together. We've got 38 milliamps and 16.2 milliamps gives us 54.25 milliamps. And that's just sort of starting to substitute stuff, and not substitute stuff, but putting numbers into variables where the variables are, like I2, and putting 38 milliamps in there, and we get these equations. By using both equations, we can verify that our calculations are correct. Always bear in mind, here there's a slight difference. I got 16.25, I got 16.2 here. With rounding up and down, you always lose out a little bit, so don't worry too much about that. Okay, let's have a look what we measured. We measured 56 milliamps for I3, and we calculated, let's have a look, 54 milliamps. So we are about 2 milliamps out. It is not too bad. When I took measurements earlier for the supply voltage, I got about 9.4 volts here, 18.1 or something for the other side. So what we sometimes get is we get variations. Also, you have to bear in mind when you look at, okay, let's look at the circuit diagram. So I got a little bit more here, about 9.1 volts. I got about 9.4, I think it was, 18.1 volts here when I was measuring it. Also, you have to bear in mind that tolerances for resistors are about 10%. Yeah, so they can be way out as well. So they can be, 240 ohms, quite a bit, or 110 ohms or 90 ohms. And they're still within spec, so they are not all spot on. Okay, that concludes the video on Kirchhoff's law. I hope it did help. The thing is, you can measure it for real. If it's a simple circuit, just make it up yourself. Get some potentiometers. If you've got some rough values, stick them on a breadboard, and you can measure it. But your calculations should be near enough. They will always be slightly different, but they should be near enough. Okay, thanks for watching, and I'll try to do another video with the same circuit, but inverting one of the power supplies. So putting the 18-volt supply the other way around, and the figure should be very different. Okay, thanks for watching.